Okay, let's get going. So here's what we've got. Welcome to Monday. Hope you're enjoying your Monday. Maybe it's not a bad idea to have all Mondays on Thursday. Maybe we'd all have a better life. I don't know. So today we are going to continue along our discussions of trees, and in particular we're going to talk explicitly about binary trees, and then even more in particular we're going to talk about these things called binary search trees, which are really the reason that we care about binary trees in the big picture. Okay, there are definitely things you can do with non-binary search binary trees, but we will talk about specifically about those. Any questions before I get going? Today I have my office hours at 7 to 9 p.m. and I will do them in the lab itself. So if you want to track me down, then you can do so in the lab tonight. Okay? No worries, Winona. Not caught on tape, don't worry. All right. So here's what we're going to do first. We're going to do a little UNIX tip of the day. Normally we do kind of utilitarian UNIX tips of the day. Today I'm going to show you one that I think is a little more fun. We'll see how it goes. And we will do that. Then we'll talk about these binary trees. We will talk about a number of different ways to actually print out binary trees. Then we'll do these things called binary search trees, and we'll talk about a whole bunch of different functions we can do with these binary search trees. Okay, and then we'll actually do a little practice on recursion with binary search trees. Okay, I told you already that binary trees are perfect candidates for recursion, and we will practice that. Okay? All right, so let's see, the UNIX tip of the day. So there is a program that I will show you. Hopefully I can connect to the internet. I was having a little trouble earlier. There's a little program called cowsay, and it happens to be on, I had to install it on the system. It normally comes with a lot of systems, but so it turns out it doesn't come directly with our homework server, so I installed it. And this is what you can do. It's in comp/15 public _HTML /cowsay, and then you say cowsay, and you can do things like, how about this? I'm a cow. Right? And when it does that, let me make the window a little bigger for us here so you can see it all. When it does that, oh, I gave it away at the top. Hang on. There we go. It'll actually say that with a little cow, right? Isn't that cute? OK, you can tell it's a cow. Is it always the same cow? Good question. Well, what you can do, first of all, is you can say, well, what if you wanted to say, let's see, I think, therefore, I cow, something like that, right? And I don't know why I didn't do it with proper English, but you can do that. And you can say, instead of cow say, you can do cow think, and it will actually, see the little like thinking bubbles there? Oh, my pointer is dying on me. There we go. See the little thinking thing there, right? So, and he's like thinking it, he's not saying it. So you can do that. There are actually a long list, comp15, public, cowsay, what is it called? Share, cowsay, the whole list of different ones. Would anybody like me to try one? Dragon and cow. Let's try that one. Let's try dragon and cow. Let's see. Hold on. Here's what you do. You say cow say and then -f, dragon and cow, and then you say something like, what kind of conversation would a dragon and cow say? Do you like my flames? I don't know, something like that, right? And there's the dragon, and the cow's not too happy because he's getting flamed right now, I think. And that's that. OK, let's see. What else would you like me to try? Vader. Let's try Vader cow. That's kind of a fun one. Vader cow. Let's see. Vader. Let's see. There's Vader. So let's see. Vader. I am your cow. Something like that, right? right? It's got a little, got a little Darth Vader thing there. I heard Stegosaurus. Let's see, Stegosaurus. Stegosaurus. And I'm not sure how many of you will get this reference, but let's do. Let's see. What am I thinking of here? So what would a Stegosaurus say? You might say, I don't even know. We never even heard what they said. Hold on, let's see. Let's say, I don't know, grr, something like that. There you go. Got a little bowler hat on there.
Where'd the cow go? Did it eat it?
The cow's gone. Yeah, he's gone. Let's see. There we go. That's what I was thinking of. Right? So let's see. So one more maybe?
Satanic cow.
Satanic cow? All right. Is it just satanic? Is that what it's called? Satanic? Ghostbusters, cool. I'll show you that in a sec. Satanic, I don't know, pitch, forks for everyone. Something like that, right? Thing there, right? It's a little 666 in there. Okay, you can actually see all of them if I wrote a little script to do all of them. And I think it's called all cow files. There's lots of them, right? Let's see. There's your Stegosaurus. Let's see. Okay, there's a Beavis. There's a couple frogs. There's a cheese for some reason. There's the demon's kind of neat looking. Looks kind of neat. Let's see. Dragon and cow is good. Dragon's really good. Elephant, the jumbo. Jumbo for you. Elephant and snake is a little odd. Right? Eyes are pretty good. Flaming sheep. Ghostbusters is pretty good. Yeah. So anyway, so those are some of the things you can do. You can look through all those if you want. And I like Vader Koala. He's kind of cute too. Very cool. Looks a little kind of neat. Let's see. OK, so that's what you can do on Linux. If you happen to have a Mac, there's actually a program called Say, which is in here, right? Which is something like this. Whoops. Uh-oh. Hold on. Didn't work very well. It's like a magician who doesn't have a good trick. Hang on, whoop, you're going to get blanked for a second. Where did it go? There we go. There we go. Now we'll try this, and we'll do the same thing again. And, oops, the same thing again. Come on. There we go. Ah, it didn't work. Hold on. Maybe. I feel bad now. It's not working at all. What's that? Is it mute? Did you hear something? Hang on.
Oh, it's muted. Yeah, your laptop.
Oh, is it? OK, hold on. Let's get this up here. Hold on. Although I don't think I need to do that. Go back.
Wake up.
Oh, no, it says it now. It said it on my computer. Hold on. Output. There we go. There we go. Sorry. I should have my demos better, like done better. There we go. No. Where is it muted now? There we go. Ah. OK. So, OK. Finally. There we go. So you can actually have it say through your speakers, which is kind of fun if you happen to know your girlfriend's SSH password and she's sitting on the couch like doing some intent work, and you can say something like, "Wake up." You know, "Oh my God, my computer just talked to me. Oh my gosh." So kind of fun. OK. Anyway, that's the UNIX tip of the day. Any questions on that? OK.
You could say, "I'm sorry, Dave."
You could say all that. Yep, you're right. OK, so that's cow say, cow think, and say on OS 10. Let's go back into some trees. Now, this is the last thing that we did yesterday, right? We actually talked about the fact that we can represent binary operations, in other words, operations that have only two operands, like A times B, in a tree. The left-hand side is one operand, the right-hand side is the other operand. OK, A times B, which is kind of neat. If we want to print out this, we showed yesterday how to print out the postfix notation, which doesn't require any parentheses. But we could use this to print out something with parentheses that would not require order of operations, but still be the regular, what we call infix notation, where the operator happens in the middle. Okay? We could do this where we have lots and lots of parentheses in there, like everything gets parenthesized, by doing this. This is a recursive function that says you takes in the root in this case. If the node is null, return. That's our base case, right? Otherwise, we print left parentheses, and then we do in order left child, and then we print the symbol, and then we do in order right child, and then we print a right parentheses, right? So let's see if it would work on this. If we start with the asterisk, we say if node is null, return. So it's not. Then we say print left parentheses. So we get a left parentheses. And then we do in order left child. There's a left child. It's not null, so we print a left parentheses, right? And then we do in order left child, but there is no left child. We come back from that. We print the symbol, which happens to be A. And then we do in order right child. And in order right child, there's no right child to A. So we return, then we print a right parentheses. And then we return from this function, which got called from the asterisk function, which means that we just did this, so we print the symbol. Hurrah. And then we do in order right, which is B. So B goes in. It's not null. Print the left parentheses. Print B, because we can't go left, can't go right. And then print the right parentheses. And then return to the asterisk, which just printed its right, so it prints the right parentheses. See how that works? Pretty straightforward. I mean, you can walk through it yourself. But that'll do lots of parentheses. We never want to actually do all these parentheses, right? Like, that's ridiculous. We definitely don't want the ones in the middle here like this. How might we amend this to do that, to have it not print those extra parentheses? What do you think? Yeah, Nathan. Don't print parentheses if the node is a leaf. So how are you going to know if the node is a leaf? Yeah, or it doesn't necessarily mean just a leaf, but it definitely is if the left child is not a if the left child is null, we don't need to bother printing the left parentheses, right? And if the right child is not null, we don't need to bother printing the right parentheses. So far, so does that make sense? Does that make sense? I might be getting that backwards, but I think it makes sense. If we want to do that, yeah, if the node has a left child, print a left parentheses. And otherwise, if the node has a right child, print the right parentheses. So those are the only times you'd actually need to print those parentheses. Good? Yeah, so that'll work. All right, so we can get rid of many of these parentheses. Why do we actually have parentheses in here anyway? Like, why do we need parentheses for these kind of arithmetic expressions? Yeah. So order of operations, I kind of got that question backwards a little bit. It's more, why do we have order of operations? What's the answer to that? Yeah.
Because if you do things in a wrong order, you'll get like wrong results. Like if you.
Well, we can define. We could have defined math to be like 5 plus 4 times 3 minus 6 is just go left to right every time, right? But the thing is, in that case, you'd need many more parentheses if you wanted to do things in the middle.
And you would also,
right?
if it was written in a different way, you get a different result.
Well, absolutely, if it's written a different way, you get a different result. But even with parentheses, that's the case. But with the parentheses, you can actually, with order of operations, you actually need many fewer parentheses. That's really what it is. So you don't have to do something crazy like parenthesize everything like this one. If we ran our algorithm through, watch how many parentheses actually come out of this one. Boom. Right? Lots and lots of parentheses. OK, let's do it without the inner, because we definitely don't need those inner ones, even if we had good order of operations. Still, see how many parentheses you get without like knowing any order of operations? These are all like the parentheses. This is fully parenthesized, right? So you'd need to do that. But if you went back and you checked the algorithm, it would do the exact same thing. How does A get printed? Why is my thing not working? How does A get printed first? Well, it goes left, and then deals with A, right? And then returns, and then goes left, and then, well, actually does this in the middle, and then goes to the right, but that has to go left, and then B comes next. Return here, print this guy, go right, print, et cetera, et cetera. Okay? This is called in order or infix notation, and you'll see in a little bit later why we actually call it in order traversal. It doesn't necessarily make much sense to call it in order traversal here, but when you see it a little bit later, you'll get why we call this in order. Okay? All right. We could also do post order, which would be like this. It would say print the operands before the operator. Okay, this is actually called the Polish notation because the guy who invented it was Polish, and it's this is another one where you don't need parentheses, but it turns out it's a little easier to do a stack when you do. Well, actually, it doesn't really matter. You can do either one with a stack, but you can do post order like that. Just you go right, go left, go right, then print out. Okay, that's how we do post order traversal. Okay. You can also go online. There's a bunch of animations. A little bit later, if we have time, I'll show you an animation online. There's some really good ones that if you're having trouble with any of this stuff, go to this website. Not necessarily this one, but there's another website in particular you can go to and like sit there for hours and like figure out how all this works by getting a visual picture of it, which is sometimes very helpful. Okay. All right. Post order leads to postfix. We talked about this the other day. That's our nice postfix representation. Okay. Sorry, I lied to you. This is reverse Polish notation because it's postfix. Okay. We also have prefix, which this is the what's called Polish notation, and this goes the exact opposite. It prints and then traverses. Okay, so that it prints first and then traverses. The only thing that would change would be instead of the cout being down here, the cout is first. That's what happens there for prefix notation. And then finally, there is this one called level order. This one I think is the most interesting one. If you were to print out a tree, you would have to print it out in level order, unless you were able to go back up the screen somehow, which you can. But in this case, you would have to go level by level. It's actually a little harder to do. The hardest part is actually spacing it out. That's the hardest part when you're doing these traversals. But this actually you cannot do using a recursive method. It just doesn't work. I would urge you to try to figure it out. And if you did figure it out, it would probably be worth a mathematical paper or something. But I don't think it's actually possible to do a recursive solution here. You can, however, use a queue to do this. Okay, let's walk through this. I want you to see how this works. In fact, you're going to do it for the lab next week, so it's a good idea to figure out how it works now. If we have a queue, okay, and here's what I'm going to do. I'm not going to put like the front and the back. I'm just going to kind of cross things out. I'm not going to make this circular just because the arrows would be all over the place, and I'd have to erase and do that. But if we were to do this in level order, here's what it would print out. It should print out the plus. Then it should print this plus and then this times. And then it should print A times plus G. See how it's going in level order, level by level, this level, then this level, then this level, et cetera? And then it would be this level, and then finally that level. So here's what you do. You have your queue, and the first thing you do is you enqueue the first one. So we enqueue the plus. Anybody want to guess what we do next? Yeah.
EQ the plus, print it, then print the left.
So
Then EQ is left and right.
I like that. Okay. DQ the plus first, which sounds weird. Why would we bother putting it into the queue to begin with if we're just going to DQ it? It turns out we're trying to set up for a little while loop. And what do you think the while loop is going to say? While what? You did it all the time. You're doing it all the time in the homework 3. What? Yeah, while not q is empty. And if we tried to start this loop with nothing in the queue to begin with, it would be done. So we put the first one into the queue, and then we immediately dequeue, right? So you basically dequeue q.dequeue, and we'll say, I don't know, character. C gets q dequeue. We're going to do that, OK? And then we're just going to print it. I'll just say print C. Print C. And then Nathan said it, but did anybody hear him what he said to do now? Yeah, what was it?
So then
you would in-queue the two children, left and then right. So it's going to be, in this case, a plus and an asterisk. And then guess what? So we're going to in-queue children. Right? And then that's it for the while loop. Right? And then the while loop is now going to start over again. And what are we going to do? DQ the plus. So far we've written down asterisk. Then we're going to DQ the plus, and we're going to write it down. And then what do we do now? What's that?
The first one you apply.
I do. Oh, sorry. Thank you. A plus, and then another plus. We got two pluses there. And then this one's been DQ'd. And what do we do after that? What's the algorithm say to do? Print the number and then enqueue the children. And the children of this plus are A and asterisk. So A and asterisk, right? And then we start over again. DQ this one, write it down, and then enqueue its children, plus and G, et cetera, et cetera. Do you see how that works? So it's kind of a clever way to do this level order printing. But basically, the idea is you need to have some first in, first out to get this one, then this row, in a first in, first out way. There's no way recursively to start here, go left, and then somehow go back right, and then go left down to this one. It just doesn't work from a recursive standpoint. OK? Questions on that one? OK. All right. So let's now talk about binary search trees. OK. What do you think we do with a binary search tree? Search for things in it, as it turns out. Right? They are frequently used to do searching, obviously. And they have this thing called an invariant. OK? Really important to know this term, invariant, because we use invariant for lots of different things. But the invariant in a binary search tree is the following. This means if the following isn't satisfied, you are not a binary search tree. The satisfying conditions are, for every node x, if you have a node, all the items in the left-hand side of the node are smaller, and all the values in the right are bigger. OK, I'll let that sink in a little. You have a tree, and it's a binary tree, and everything to the left has to be smaller than whatever you are, no matter where in the tree you are. Everything to the right has to be bigger, no matter where in the tree you are. OK? This isn't called an invariant, and an invariant means that this is satisfied for the data structure. Yeah, Isabel.
So aren't we used to invariants like all the time? Like we have, whenever we set like a certain way of function, like whenever we think about a program or a function, we think of like, in what cases does it always need to do X, Y, and Z?
Yes, you see invariants in a number of different ways, yeah. In terms of a data structure, for the binary search tree, if it doesn't meet this, it's not a binary search tree. It might be a binary tree, but it's not a binary search tree, for instance. OK, questions on this? Let's see an example. OK, the tree on the left is a binary search tree. The tree on the right is not a binary search tree. Why is the tree on the right not a binary search tree? Yeah. Because 7 is greater than 6. And 7, 8, 9. It's a joke. Anyway, yeah, Sarah.
And this would follow for each.
Wait, hang on. Why was 6 afraid of 7? Because 7, 8, 9. That's the joke. Anyway, sorry, go ahead.
So each subtree that's true for the root of that subtree as well?
Yes. So wherever you are, everything to its left has to be smaller. Everything to its right has to be bigger. That's it, right? And so you can see, so 7, even though it's technically, like, if you look at it, it's actually falls rightmost of 6 because of the way I drew the tree. It is in the left path of 6. So therefore, because 7 is in the left path of 6, it's not smaller than 6. Therefore, this is not a binary search tree. Right? 2 is fine. 1 is fine because it's less than 2. 4 is fine because it's less than 6 but greater than 2. 3 is fine because it's less than 4 but greater than 2 but less than 6. And 7 is not fine because it's greater than 4, greater than 2, but not less than 6. Yeah?
So each node not only has to satisfy those conditions for itself, but also the ones above it.
Yeah, absolutely. So wherever you go in the tree, everything to the right is bigger, everything to the left is smaller. OK? And it will always, and then if you do that, you've got a binary search tree. OK. So binary search trees, the depth of how big they are, the height or the depth, whichever you want to talk about it, is generally logarithmic if we have a nice-looking binary tree. OK? If it's what we call more or less balanced. In other words, the stuff on the right is about the same number of the stuff on the left. This is a logarithmic number of steps to go from the top to the bottom, which is awesome. Why is it awesome? Because we love logarithmic behavior. OK? If we have logarithmic behavior, then for 1,024 items, if you're trying to search for something, on average, you will only have to search 10 times to find it. So that's kind of nice, right? If you have logarithmic behavior, right? And if you have 2,000 items, you only have to search 11 times. So doubling the amount only makes it go up by one thing. So it's actually really nice because it generally is logarithmic. Now, it's not always logarithmic because you can arrange a binary search tree. If I have a binary search tree and I put 1 in it, no, let's say I put 1 in it, and then I put 2 in it, where's 2 have to go? To the right. And then where's 3 have to go? To the right of that one, and then 4. And so you can construct a binary search tree. This is a binary search tree, but it's a very degenerate one. It's not a very balanced one. And so we don't like these, right? If we had done it a little bit smarter and said, well, let's not put 1 in first. Let's put 3 in first. And then we put 1. 1 would go over here. And then where would 2 go? To the right of 1. And then 4 would go to the right of 3. So it's a little more balanced that way. Next week, we will talk about how to make more or less balanced trees. OK? Yeah?
So it's the same speed to search as a sorted array?
On average, it's the same speed to search in a sorted array, which is why we call binary search trees or binary searching through an array. OK? That's what we do. An alarm, or is that a someone's calling you? OK, please put your cell phones on mute or vibrate or whatever it is. OK, so anyway, logarithmic is very nice. Now we will talk next week about how to try to assure that we get logarithmic behavior, because we can make it so that it's not logarithmic. OK, this is kind of the fun part. We are going to define a number of functions for a binary search tree. Now, people always ask, hey, is a binary tree a data structure or an abstract data type? And my answer, I kind of hedge my bets on this a little bit. I say that a tree is a data structure. In other words, a tree has nodes and so forth. But a tree and a binary search tree is kind of more of an abstract data type in that we define all these functions on them. OK? The abstract data type, you can have an array that has all these functions as well. So that's the abstract data type part. But the fact that it's a tree structure is the data structure part. OK, I won't ever ask you to differentiate, but just kind of think of it on those terms. This is one of those hazy ones where it's kind of a little bit of both. OK? What we can do is we can define these methods. And I've got 4 which I'm calling the easy ones, and then a 5th one which I'm calling the hard one. And we'll get to the hard one in a little bit. But here's what I want you to do. With your neighbor, try to figure out how I would have a function, preferably recursive, to actually find the minimum of a binary search tree. OK? And then if you figure that out, do find max. And if you figure that out, do contains. Don't worry about insert quite yet. OK? Say again? They're probably easiest to write recursively. First, define how you'll do it. Then talk about the recursive part. OK? Good. OK, who thinks they can do find min? How do you actually do it? Email.
So the base case would be the left pointer is pointing to null.
OK, so we do have to have a base case. I like that. If we're going to do this, recursively, so if n left equals null, what are we going to do? Return whatever we are at. Return n, and we'll call it data. OK, so that's first. You're going to have trouble with this one if you pass in a null tree. What do you have to first check for? Yeah, so let's do this. Well, the problem with that is there is no min. So actually, you'd have to have some sentinel value. So let's not worry too much about that. But if you do have the ability to send back a non-integer value or something like that, then you could do that. But OK, I like that. What do we do then?
You call
Find min and left. Is that it? We missed one thing on here. Return find min. Right? Because you have to return the value that you're going to eventually find. OK, yeah?
Quick question. I'm never concerned. What if, per se, you have a node that goes to the right? So like we have 4, and we have 3.
Give me the example. Can you draw this out? Can you tell me what it would look like?
So like our top node is 6.
6.
And then to the right is 8.
OK.
To the left is 4.
To the left of which?
To the left is 6.
Is 4. OK.
Then you have, like, to the left of 4 is 2.
OK.
To the right is 3.
To the right of what?
4 is 3. And to the left of 3 is 1.
To the left of 3 is 1. What's wrong?
That's not binary.
Not a binary search tree. Why isn't it a binary search tree?
Because 1 is to the right of 4.
Because 1 is to the right of 4.
Okay.
See, because it's in the right-hand path of 4, so it's not a binary search tree to begin with.
Okay.
Right? So,
So what if that was like,
yeah. Yeah.
What happens in a binary search tree if you try to put 2 values that are equal? Like if you put in 3 twice.
Very good question. Very good question. Before I get to that, does anybody have any questions on this? We basically go left until you find the minimum, right? Find min, start at root, go left until the node doesn't have a child, and we'll get to find max in a sec. To answer your question about what happens when you insert into a binary search tree the same value that's already there, you have about 3 different solutions. Solution 1 is you don't care if it goes left or right, make it either. That's solution 1. Doesn't really matter. Like in the end, it will all work. Most things will still work out just fine. So you can add it either to the left or to the right, won't matter. OK? Second, you just have to be consistent throughout your rest of your, with all your inserts that way. OK? Second thing is you could just set a little counter inside the node that says how many you have. So if you get to 1 and you say, oh, I'm going to insert another 4, oh, now I've got 2 4s, and remember that. And everybody else is going to be 1. So that's the second way. The third way is just to get to a point where you're inserting it and say, oh, I've already got 1, ignore it. See how it works? So you can do lots of different ways. We will, the next homework assignment is on binary search trees. And we will, you will have to handle duplicates with a little counter. OK? So good question. All right, so we did find min. What's find max? Same exact thing, except you go right. If node right is not equal to null, or is equal to null, return the data. Return find min node right. Done. OK? Keep these in mind in a few minutes, because we will use this extensively in a few minutes. Let me just, first of all, if you go all the way left to find min, what does that mean about the number of children that the last one actually has, that the minimum has? It has either what? 1 or 0. It cannot have 2 children, because if it had a left child, we'd keep going down, right? Because that would be less. OK, keep that in the back of your mind for a little later. OK, so find max, exactly the same. Start at the root, go right until the node does not have a right child. Done. OK, did anybody get to contains? This one's a little bit trickier. A little bit trickier. OK, let me write this down. I will try to do my best, and if you guys tell me what it is, I'll try to get it right. But let's see. We're doing contains. So we need to have, instead of int, we're going to have bool. Because it's going to be a Boolean value. Boolean contains the node. And then let's say int a. OK, what do we think we have to do for this? What's the general idea before anything? Winona?
Well, the general idea is just going through the node, like starting at the root. You go, OK, is this the number I'm looking for? And if not, then you go, OK, is it bigger than or smaller than that node? And if it's smaller, you go left. If it's not, you go right.
OK. And when would we return false?
When the leaf, the last node you go to, so say you go to 1 and the number you were looking
OK. How about this? Can we say that if we're calling contains and we call it on some node and it's null, return false? Can we try that as a base case? Let's try that. So basically, if node equals null, return false. OK, because that will actually work if we're going to try to do a base case. I like that base case, because then it'll say no if it's an empty tree, which is a good thing. OK, it'll say it does not contain it. OK, so then you're saying we have to do some check on here. OK, let's do the case where it is the one we're at. What do we do? If yeah, if no, oh, I just did call it no n, didn't I? N, if n data equals a, return true. OK. What next? Else if. You know what? We don't even really need an else, because we're definitely going to return the else is going to happen. But you could put it. If not, wouldn't criticize you did. But OK, let's just not bother. But what are we going to say? If n is if n data is smaller than a, what are we going to do? Contains, and then n left, sorry for people who can't read, comma, a. Same thing. OK, I like that. And then what else? Same thing for right. If, well, I'll just write it. If n data, or do we even need an if at this case? Probably not even. We probably just need an else, don't we? Or just a return. Return contains n right, comma a. Will that do it? Yeah, there we go. OK, so you have to do a little check. But basically, this is where you're cutting the problem into not necessarily halves. If we've got a very balanced tree where half is on half on one side and half is on the other, then it does cut it in half. But basically, you only have to go down to you only have to go down, on average, a logarithmic number of steps. OK, so this is a very nice kind of logarithmic on average algorithm. What's the worst case algorithm for this? Yeah? Oh, did I do it wrong? If the data is smaller, if the data in here is smaller than a, we do want to go right. Thank you. Let's see. I'll do it this way, right, and this one's left. Thank you. Got to think about these things. OK, back to my question. What would for any tree that you can think of, what's the worst case search for that? I'll asymptotically. Linear. Why? You can end up with a linked list, so you're still going to have to go left, 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 left all the way down, or whatever. Right, or left, right, left, right. And if those are the only nodes, then it's going to be linear. What's the best case?
0.
Well, 1. You still have to do a check. We'll call that constant behavior. OK, good. So that's contains. Basically, does the tree contain x? If it's empty, return false. If it is x, return true. Otherwise, recursively call t left or right, depending on x's relationship to t. Very good. OK. All right. How about insert? This is where we're going to insert. Let's let's not worry about ties right now. Let's just say we're going to insert into a tree. Okay? How might we do this? You want to think about it for a minute? We got time. Think about it for a minute. Okay? I know you got it. Think about it for a minute. Okay? Talk to your neighbor about it. You can converse about it. Ignore that for now. OK, who thinks they have an answer? I know you have an answer. I know you got it. Let's see if someone in the back row has it, or someone near the back has the answer. What do you guys think back there? Yeah, go ahead.
We were thinking that you could pretty much just use the same formula as contains, except instead of returning false, if the node is empty, you could just put the number there.
Yeah, you have to be a little bit careful, because much like with linked lists, if you're trying to insert it at a linked list and you've gone too far, there's no like parent pointer generally, right? So you have to be a little bit careful with that. So it's not going to be just if n equals null, return false. It's basically going to be you're going to do a check to say what? If like you do the check about greater than or less than, and then you do one more check, which is what? If the child that you would go to is null, put it there, right? Does that make sense? So you're basically going to do the right idea. Is that what you had? Yeah, you guys said that? OK. Basically, it's similar to contains. If t is empty, that's the root. There's your special case. OK. T is empty, you're going to insert at the root. If t is the number, OK, this is the special case. And this is where you would have your duplicates list, or just put it left or right, or whatever your decision is, or skip it. And then you recursively call either t left or t right, depending on the x's relationship. Right? And I guess what we didn't quite say in here is check before you do that recursive call so that you can actually insert at that place. But the idea is, let's say we were inserting 5 into this tree. Is 5 less than 6? Yes, go left. Is 5 greater or less than 2? No, go right. Is 5 less than 4? Yes, go left. Is 5 less than 3? Sorry, I lied. Is 5 less than 4? No. So does 4 have a right child? No. 5 has to go right there. Thank you. Question? Was that the idea? So do you ever need to break any nodes up to do inserting into a tree? What do you think?
Oh, no, that's the question.
OK.
I think you don't need to break it up.
OK. Go ahead. What's your question?
Do you always insert a node into a tree at the highest possible level?
You insert at the only possible level.
Because, for example, let's say there's a tree with a root 6.
Let me write this down. Tree with a root 6. Got it.
Its right child is 7.
OK, hold on. Right child is 7. Yep.
7's left child is 8.
7's left child can't be 8.
Oh, no, sorry. It's like,
Is 9? Can't be.
no, the root is 5. The root is 5.
OK, hold on.
The root is 5.
Now you're confusing me. The root is 5. OK. Root is 5.
The right child is 7.
Right child is 7.
The left child 7 is 6.
Left child of 7 is 6. OK.
Insert 9.
Insert 9. There's only one place for it to go.
Okay,
Right? It's got to go. It's bigger than 5. It's bigger than 7. It has to go right there.
so there's only one place for every.
Only one place. Yep, there's only one place on any tree. And you never need to break things up because you'll always either go left or right. OK? So that's why it makes sense. Yeah?
What if you want to cut something from it?
Well, we'll get to that. We'll get to that. That's the one that we said was a little more difficult. OK? Everybody get this, though? Basically, go until you get to a null place where it would go and put it there. Yeah, Katie? Yeah.
I mean, you can change that tree, right? So it's more balanced.
You could. You could change it so it's more balanced, yes.
Would you want to do that?
No. We're not going to. We're just simply saying, don't worry about the balance now. Next week we will talk about after we insert maybe balancing it, right? But don't worry about balancing it now. Good question, right? But right now we just want great behavior. The behavior is logarithmic for this too, right? Because you basically have to go either left or right until you get to where you need to go, and boom, right? So it's actually pretty good behavior altogether. Question? Yeah, we've already talked. So if there's 2 6s, you basically either say, put a counter that says there's 2 6s, or ignore it, or put it either left or right. It will probably work out. Just be kind of consistent with that.
So it's
Okay?
it is considered binary even with even
Yeah,
with
it's still considered a binary search tree.
so
Yeah,
it can be greater than or
greater than or equal generally, yes. Yeah. Okay. Other questions? Okay. Yeah. Okay. Why not? We could put -1 in this. Where would it go? It would go to the left of 1. Yep. Good. Yeah. Sure. You can do negative numbers. Yep. You can't.
Go complex.
You probably can't go complex. I was just going to say. Yeah, I don't think you can go complex because there's no. You can do whatever you want as long as you can compare them. So as long as you can compare 2 things, then you can go. They can go wherever you want. You can have whatever you want. So strings, for instance, you could have a binary search tree full of strings where you're comparing them alphabetically. That would work fine.
what if you had a compare function?
If you had a compare function and it does something logical, in other words, you can't say, is A less than B? Yes. Is B less than A? Yes. Like, that's not logical, right? But if you had it logical, you could do it, sure. Anything where you can do a compare, you can put them into a binary search tree. OK, good. All right, we're done with the easy ones. Woohoo! OK, oops, there you go. If node traverse to is null, insert. That's the one we forgot. So we already talked about how to insert 5. Remove. OK, here's what I want you to do. Remove is an interesting function. Because what remove does, for instance, we could remove 3. OK, we could remove 3. We could remove 4. We could remove 2. You have to figure out the various cases of how you do those and what you actually do to remove those. OK? First, the first thing you do is you think, this is easy. And then you go through it and you go, oh, it's a little harder than I thought. Right? So try it with your neighbor. Take about 5 minutes or so and like hack away at this a little bit and try to figure it out for the various cases. OK? You guys have a question?
The linked list that we have with the card project.
No, I think there's
It's more advanced than that. Try it.
Well, I mean, other than having.
No, I think there's a way easier way to do it. Because you think about it, if you can somehow make it it's left and right, then you can say remove it and
One child.
then insert left.
Yeah.
Is it remove like the particular node?
So I want you to, like, if you're going to remove 4, you have to. If you're going to remove 4, 3 still has to be in the tree.
Yeah.
Yeah.
What was I saying? Should we return the node after? Return the node
It's up to you. Sure. Yeah. I mean, but I'll basically say you could either do that or you could say true or false as to whether you returned it. But I'm not too worried about that part of it. Just get the algorithm right first of all. Aye. Good. Don't cheat and look ahead. What are you thinking?
Well, I mean, I'm thinking more of a 2 standpoint. Like, if you were moving to 6 would point to 4, 4 would have to point to 1, and then you have to.
Well,
compare the
be a little careful. When you say point to, make sure you say left or right, because there's no, like, can't just say point, right?
Yeah,
So it's,
this is left child.
Yeah.
Point to 4.
okay.
And then, like, 4 would have to point to 1.
Which one? 4 is left, okay.
But then 4 would have to compare whether or not 3 is.
Yeah.
No. 6 would point to 4, and then 4 would have to compare whether or not 2's left child is greater than 4's left child.
It's kind of complicated, isn't it?
Yeah.
What are the easy cases?
The greatest and at the end.
The greatest and at the end. How about just a leaf? Leaf's easy, right? Okay. What's the second easiest case? What do you think, Alex? Yeah. If you try to do arithmetic with null, depends what you mean. If you try to do it with a null pointer, you'll generally have a segfault. If you try to do it, null happens to be equal to 0, so you could probably do something, but the compiler would complain probably. Yeah.
Complexity just go up with every level, like from the leaves up.
Yeah. Yeah.
It's worse.
Yeah. Well, kinda. Kinda. But it's not so bad though. When you see the real thing, keep trying for another minute. Yeah, Josh. No, everybody else remains.
Then what's your starting point?
What do you mean? I want to remove some number, and I say remove 4. I remove 6. I remove, yeah. We have a root pointer, which points to the root. It's kind of like the head of a list, but it's called the root pointer.
So what would be the new root then?
You tell me. We'll figure it out. We'll figure it out. Keep thinking. Okay. Have people figured out some things? It's a little harder than you think, right? Maybe it's not. Maybe you're like, woo, super brainy or something. You figured it out. Awesome. Which is the easiest case? When the node is a what? A leaf, right? If we're going to remove 3 right now, what do you have to do? Delete it, right? You just have to make 4's left point to null, delete 3, and you're done. Right? That would be easy. So leaves, super easy. What's the second easiest case? One child. Because if there's one child, let's say we were removing 4. This looks a lot like doing what? A linked list. Don't we just have 2's right point to whatever 4's child is? Right? Doesn't matter if it's it doesn't matter if it's bigger or smaller. It's going to be to the right because everything here is bigger than 2. Okay? And it doesn't matter if it had. It also doesn't matter if it had lots of other things on it. 2.5, 2.7. Doesn't matter. This one still points to this, and everything else is still perfectly fine. OK, so those are the easy cases. OK, what's the hard one? 2 children, right? 2 children's hard. So if we're trying to delete, in this case, the number 2 here, we've got a whole bunch of choices we have to make. Does anybody think they have a good way of doing it? What do you think?
Okay, well, first thing to do is you would take that place and put 4 in it.
So let me rewrite it over here. 6, 8, and then you're saying make that one 4. OK.
And then you would also transplant its left node to the new left node.
So 3. And then what happens to the 1?
You would keep a pointer to the 2 and stick it off to the left.
But what if this had let's see. So you're saying put this one always to the left? I'm not necessarily. So down here, you mean? Like that?
The 2. I mean, you put the 1, yes.
The one there?
You do the left after the node. After the leftmost node of the 4. You keep going.
OK. OK. What happens if it looks like this and we're trying to remove 2? Same idea? OK, can you clarify that? I'm not sure that's going to work in every case easily. Because you've got to have this one, and this one's got to bump into this one. So you've got to go down however many. Like what if, I should have said, what if it's like this? What if it's 3, let's say 2.5, 2.1, 2.4. What happens there?
It always goes
You always go all the way to the leftmost node. OK, I think that'll work. I think you're on the right track. I think that's not quite as easy as one I'm going to propose a little later. But that's not a bad solution. OK, let's see. We still got there. OK, who else has one? Somebody, well, yeah, go ahead.
So
Alexander.
I'm not sure how efficient this is, but
OK.
I thought if you made a temporary stack.
OK, you can make a stack.
Yeah, so we took so say we were trying to remove 2 for example.
Yep, we're moving 2.
Take the left node first and put it on the stack.
OK.
And then you go to the right node and take their children depending on how many it had. And
So what if this was 1.5?
yeah, I guess the recursive function.
OK, you're recursive, and then OK, so you've got 1.5 in here and 3 and whatever. OK, and then what do you do?
And then the last one you would put on the stack would be what would replace 2.
Which in this case would be what?
4.
Forget about this. OK, 4. And then you'd end up with basically the same one as these guys had. When you replaced everybody, is that what you're popping off the stack to do it?
And then you'll pop off the stack and using the insert function, it'll do it like in the correct order for you.
If you go and insert again. That probably makes sense. I think that would work. Problem with that is you're going to do a lot. You are going to do a lot of recursive and a lot of like work to do it. But that might do it in the end. That might do it in the end. Sarah, what do you think?
You replace the node you're removing with the leftmost node, and you call remove on that leftmost node, and then keep going.
Say again.
You replace the node you're removing with its leftmost node, the leftmost child, and then you call remove on that leftmost child, and then keep going.
0.5, 0, 0.2.
2 becomes 1.
2 becomes 1. OK. And then what? And that.
You would call remove on 1. And then keep
What if 1 had what if it had a 1.5?
Then 0.5 comes up to where 1 was, and it still keeps being true for binary trees.
It'll still keep being true. I think it's a little messy. I do think it's a little messy. But I like the idea of saying going to a minimum one or something like that. OK, one more idea. Yeah, we haven't heard from you like that.
If you remove 2,
Yep.
and you can make the right node of the left child, or if you were removing 2, you can connect the left child of 6 to 1.
The left child of 6. That is left child of 6.
Yeah.
Oh, you mean OK? You mean replace 2 with 1?
Yeah. You replace 2 with 1.
OK. That would work. But what if there was a 1.5 here?
Then you could still keep the.
Yeah, it gets a little crazy, doesn't it? Let me propose one other thing to you. OK? Let me propose one other thing to you. 1 and 2. Turns out, so we know this are the easy cases. We've done the easy cases, right? If it's a leaf, we're done. If it's one child, bypass, like the linked list. OK? If it's the 2-node case, let me propose this. And there are other solutions. The one that I'm going to propose is actually fairly straightforward. The node you want to remove, find the minimum of its right child. The minimum of its right child happens to be this one. OK? Replace this number. Don't worry about breaking any links yet. Just replace this number with this guy. Now, what do we have to do? We have to remove this one, right? And what is definitely true about the minimum in any subtree? It's not necessarily going to be a leaf. This could have 3.5. It's going to only have, at most, 1 child. Because it's the least, if it had 2 children, there would have to be a little smaller one, right? So in this case, so how easy is it now to delete 3? Doesn't it only have 1 child? And deleting 1 child is pretty darn easy. Recursively call delete on this one. And all that has to happen is 4's left goes down to there, and this one's gone. See how easy that is? So let me reiterate it. Actually, I think it's up here. If a node has 2 children, replace with the smallest data in the right subtree. In other words, find the smallest data, not necessarily the node, just the smallest data in the right subtree. replace it, and then bypass and then delete this one, which is easy to do because it either has no children or it only has one child. Okay.
Would you call it like find min on just the 4?
Absolutely. Call find min on the 4 and use that data, put it there, right? And then you need to call remove that, and then you remove that data from 4, and you're done, right? So it's so easy. Yeah. Yeah, that is a little bit tricky. Keeping track of the previous one's tricky. It's similar to a linked list in that you have to be like thinking one node behind. But that's about it. It's not too bad. Not too bad. Okay. Technically, you could have like parent nodes as well, but you don't want to go down that road if you can help it. Like trying to keep all that updated is painful. Painful. Question? You got a question? Let's try it with the root. Let's say we were going to remove 6. Let me do this. Let me say 9 and, well, let's make that 19 and then 10. OK? Let's do it for this case. And then let's do 9 to 9. What am I going to do there? 10? Would that work? No, it's got to be between. I did this wrong. You guys have to fix me here when I do something silly like that. Right? That can't work. Oh, it's 19. It was 19. Sorry, I said 19. OK. We'll make that 20 and then 10 and then 12. OK. So let's do it for this one. OK, let's actually do this. So let's remove 6. OK, what do? We find min on the right child of 6, because it's a double, because it's got both left and right. Boom, boom, boom. There it is. OK?
Min of the right child is the min of the right child of 8.
No, the min of the right child. Oh, sorry.
Yeah, because you can't go left from 8.
Did I do anything else? Oh, you're right. So that's, let's see. So oh, you're right. So that's actually easier, right? It is pretty easy, actually. So it's 8. Thank you very much. So you take that data, and you go. I meant to put it up here, but that's all right. Put that there, OK? And then we're just going to remove 8, which basically is easy because we know that 8 does not have a left child. So we have to just make the original, this 8, get bypassed like that. Done. OK? Works perfectly well with this. Yeah?
So if, in that case, would we need to write another base case to ask if the node that needs to be removed is the root? Because the root has 2 children.
The root does have 2 children in this case. Yeah. Well, it's a special case in that you're going to have the root pointer pointing to. You need to update the root pointer. Yes. You will get much practice in this on the next homework assignment. I guarantee it. OK? Questions on that? If this doesn't quite gel yet, go back and look at it again. Try it out a few times. But follow this algorithm, and it will work every time. Yeah?
Will the homework be due at the same time?
I haven't decided yet. Will the homework be due at the same time? I haven't decided yet. Probably not, because I haven't assigned it yet. So I'll probably give it a couple extra days. I just don't want to get too far behind. That's all. OK. How to remove 2? We talked about that. To remove 2, we would go find the minimum of, why is my pointer not working? There we go. The minimum of the right subtree, which is 3. 3 goes there. And notice something. This, if it's the minimum, everything else on this right tree has to be bigger, because it's the minimum. And it's still bigger than everything on the left. So that actually is another good way to kind of think about it. OK? So 3 goes here. And then we just have to bypass the left now of 5 gets the right of 4 because it was the only child. OK? All right. Now, we've got about 10 more minutes. Let's do this. Let's practice a couple of recursive functions. OK? Given a binary tree, count the number of nodes. Don't count the amount of each. Just count how many total nodes there are. So for this one, we would count 1, 2, 3, 4, 5, 6, 7, 8. OK? All we want to do is not in that order necessarily. You just want to count how. What I'm going to do is on this tree, I am going to say size. I'm going to say int size, right, of node n. And I want you to write the actual function, which says how many nodes are in here. OK, give that a shot. If you figure that out and talk to your neighbors about it, that's cool. If you get that, go to the next one and try to find the max depth. In other words, the longest path to the bottom. So for this tree, it would not be 1, 2. It would be 1, 2, 3. OK, you can do this recursively relatively easily too. Okay, I just want you to practice a couple of these, and I'll show them to you. Look at this chalk all over me. I'll start you out. I'll do it over here. Int size. Get that first? Does that make sense? All right. The other one was max depth. If you get done with max depth, try to do this one, print tree. This is the one that we want to print in, let's see, 1, 2, 3, 4, 5. This was in order. Remember our in order? 1, 2, 3, 4, 5. In order. If you get done with that one, here's the tricky one. Mirror. Change the left tree into the right tree using a recursion. It's actually kind of tricky. But try the other ones first. Try max depth if you haven't done that one yet. How's that look? What's that? Intense. The hard part about recursion is thinking about like how this pans out for a real problem, right? You basically say, if it's null, return 0. We get the right depth, right? Which means we call this one, and this one's not null, so we call right depth, which is null. So we have to return 1 for that one, right? Actually, I lied. We have to do, no, we don't. We have to figure out which one's bigger. We have to call right and left, and so it's going to be this one, right? So this one, because the left is going to be bigger, so this one's going to call right and left, and this is going to be bigger. This one's going to return 1. This one's going to return 1 plus 1, 2. This one's going to return 3. This is going to get up to here, and it's going to be 4 on this side. This one's going to return 1 and 1, so this one returns 2, and this one returns 1. That means this one's bigger, so the 2 wins out over the 1, and then 2 plus this one is 3. But guess what? The 4 wins out over the 3. So you see how that works? It's a little bit, it's definitely tricky, but it's a nice, relatively easy recursive program. Okay? I will go ahead and post the answers to these online, so you can take a look at them and look at them. But that's that. Okay? All right, any questions? Remember, there's office hours tonight, labs tonight, and homework is due Sunday at midnight. See you guys later.